everyone, thank you for joining this lesson. Today we're going to learn about ionic bonding, and these are the learning objectives. The first is to know that ionic bonding is electrostatic attraction between positive and negative ions. We're also going to look at dot and cross diagrams, the explanation of solid structures of giant ionic lattices, and the explanation of the effect of structure and bonding on the physical properties of ionic compounds. Now we're going to look at what happens in ionic bonding. So first of all, ionic bonding only occurs between metals and non-metals, and that's because electrons are transferred. So electrons are transferred from metals to non-metals. So metals form cations, so they become positive, and non-metals become negative. So they become negative ions, and they become positive ions. So if we have a look at the example of sodium chloride, sodium, the atom, has 1 electron in its outer shell, and chlorine in the outer shell has 7. And so this 1 electron here gets transferred to the chlorine atom, and so they form an Na plus ion and a Cl minus ion. So the metal becomes a cation and the non-metal becomes an anion. Also, there are strong electrostatic forces of attraction between oppositely charged ions, which extend throughout the whole structure. And it's really important to get the wording right. So it's very strong electrostatic forces of attraction, and you have to include between oppositely charged ions and not particles, because all of the particles in the structure are ions, so you need to be really specific. And I always like to put which extend throughout the whole structure, kind of just to say like the whole thing is strong and the attractive forces are in the whole entire thing and not just in like a little bit of it. So they form giant ionic lattices, which are solids at room temperature. They're brittle, they have high melting and boiling points, and they can conduct electricity when molten or aqueous. So we're going to go through that. They can conduct electricity when molten or aqueous because when it's molten just means when it's melted, there are ions in the lattice, so they can conduct electricity, because the two ways you can conduct electricity are either by delocalized electrons, which are just electrons which are free to move without the whole throughout the whole structure, or ions. And because ions are present, we can conduct electricity, and we can also conduct electricity when it's aqueous, meaning dissolved in water, because then all the ions are like free to move, so you can conduct electricity. They have very high melting and boiling points, and this is because of the strong electrostatic forces of attraction between the oppositely charged ions, which extend throughout the whole structure. So whenever it asks for why it's got such a high melting and boiling point, you can just quote that sentence, and that should get you the marks. They can be brittle sometimes because they're like just by how it's arranged. So you have alternating cations and anions, and sometimes when you push them, they can just kind of slide over each other. They're usually solids at room temperature just because of the high melting and boiling points again. So room temperature isn't high enough for it to melt into a liquid. Now we're going to figure out how to draw a dot and cross diagram for ionic bonding. So our example is magnesium chloride. Magnesium is in group 2 and chlorine is in group 7. So I start off by just drawing out the dot and cross diagrams of magnesium and chlorine. So magnesium, we have 3 shells. So in the first shell we have 2 electrons. Then we have 8. and then we have 2 on the outside. And then I'm going to draw some chlorines. So it also has 3 shells. First shell, it's got 2 electrons, and then we've got the 8 in the second shell. And then we have 7 in the third shell. Okay, so now I've drawn them out, I can kind of have a look at what each of them needs for a full outer shell. So I can see that magnesium has these 2 extra ones here that it kind of doesn't really need for a full outer shell, because that's the easiest way to get a full outer shell. So the 2 ways in which you can get a full outer shell is either to add 6 electrons or to take away 2 electrons. So the easiest way is to take away the 2 electrons instead of adding on 6. And for chlorine, I would say that we need 1 electron here for a full outer shell instead of taking away all these 7, because that would take a lot longer. So that means that we would need 2 chlorine atoms for every magnesium atom. So if I draw another chlorine, let's put in the electrons. So then we can say that one of these electrons gets transferred to 1 chlorine. So it gets transferred to 1 chlorine atom. So that's 1 electron, and this is the other electron. And so they both form ions, which then have full outer shells. So these ions then look like this. The magnesium will be a magnesium ion, but it's lost 2 electrons, so it only has 2 shells now. And it still has 2 in the first shell, and it still has 8 in the second shell, so that hasn't changed. But it now has a full outer shell, so a noble gas configuration. And all atoms actually want this because they're more stable when they've got a full outer shell. So then this becomes a 2+ ion because it's lost 2 electrons. And then we have the 2 chlorines, which have now become chloride ions, and they have an extra electron each. So if I draw it like this, and this is just to signify the extra electron, then that forms a minus ion, and then we have another one of these. So I'm just going to put a 2 in front. So we get 1 magnesium 2+ ion and 2 chloride 1- ions. We don't need to put the 1 just because it's normal just to put the minus. And that's how magnesium chloride is bonded. Now we're going to look at some questions. So the first one is to predict which one of the pair has the strongest ionic bonding and explain why. So A is sodium fluoride or magnesium fluoride, and for B, aluminium oxide or sodium oxide. So first we'll have a look at sodium fluoride and magnesium fluoride. So they're both reacting with fluorine atoms, so we kind of just ignore that, and we're comparing sodium, the ion, and magnesium, the ion. So sodium has 3 shells, and the outer electron is in the third shell. And magnesium also has 3 shells, but it has 2 electrons in the outer shell. And so straight away we can see that sodium would form Na plus ions and magnesium would form Mg2 plus ions. And so from that we can see that the ionic bonding between magnesium and something compared to sodium and the same something would be bigger. And now we're going to have a look at the size. So the size is actually pretty similar because they both have the same number of shells. So overall, the magnesium would have a lot would be a lot stronger bonding to the fluorine atoms to form magnesium fluoride because the ionic charge is bigger than in the sodium ion. And then for B, we have aluminium oxide or sodium oxide. So this is a very similar thing. So we ignore the oxides because they're both the same. And then we have a look at aluminium or sodium. So aluminium is also 3 shells, but it has 3 electrons on the outer shell. And so from that, we can see that aluminium forms 3 plus ions, and the size of it is quite similar to sodium and magnesium because they have the same number of shells. And so we know that the ionic bonding in aluminium oxide will be a lot bigger than sodium oxide. So for the first question, magnesium fluoride is the answer. And for the second question, aluminium oxide is the answer. So number 2, explain what the formula of Al2O3 means. Feel free to click off the video and try it first. But this one's a bit confusing because it comes up sometimes and it's quite hard to know what they kind of want from the question. But they're just asking what it means for there to be 2 aluminium ions and 3 oxide ions, basically. So what you need to answer is that because aluminium forms 3 plus ions and oxygen forms 2 minus ions, that means that we need 2 aluminium ions for every 3 oxide ions. So the ratio is 2 to 3. So that's why we have Al2O3. This is a format of a question which is probably quite useful to remember because sometimes it can kind of trip you up, because it's a bit confusing, really. Hi everyone, welcome to the video. We're going to go over some harder questions for ionic bonding. So these are questions which will generally come up in exam papers. So the first one is that sodium sulfate has a melting point of 1223 Kelvin. Predict the type of bonding in sodium sulfide and explain why its melting point is so high. So firstly, we look at sodium sulfide. So sodium sulfide is made up of sodium and also sulfate. These are the original atoms. And we can tell that sodium is a metal because it's in group 1, and sulfate is a non-metal because it's in group 6. And so a metal and a non-metal, that implies that we have ionic bonding. Explain why its melting point is so high. So we know that with ionic bonding, we have giant ionic structure. So we have strong electrostatic forces between oppositely charged ions. So that all of that means that we need a lot of energy required to overcome the ionic bonds. So things to remember are that it's giant, that there's strong electrostatic forces, and also between oppositely charged ions. So that they would be your kind of 3 marks there that you need to tick off. So keep in your mind a checklist of everything that you need for ionic bonding. So giant structure, strong electrostatic forces, oppositely charged ions, and also a lot of energy required to overcome. So those are all the reasons why the melting point is so high. And if you hit all of those 3, then you should get all the marks. And for the second question, compare the electrical conductivity of solid sodium metal and solid sodium chloride. We're actually going to go into this in a bit more detail when we do metallic bonding, but sodium metal is actually metallically bonded, and sodium chloride we know is ionically bonded. And because it's ionically bonded, that means that it can only conduct electricity when it's molten or aqueous, and that means that when it's melted or when it's dissolved in water. And this is because the ions then become delocalized, so they can move around, so they can carry the charge, which conducts electricity. But with metallically bonded compounds, such as sodium, they already have a kind of sea of delocalized electrons, so electrons which can move and carry the charge. So they can conduct electricity even when they're solid. So that's the answer to that question. But we will go into further detail when we do metallic bonding.